Hi guys, so today we'll be going through kinematics and I'll be helping you to derive the equations of motion. We're going to derive all three equations and we shall use some concepts of calculus. So we know that acceleration is velocity over time, while velocity is displacement over time. So let's start with acceleration. We know that acceleration is the change in velocity with respect to time, right? So if I cross multiply, this will give me dv is equals to a dt. So on the left hand side, I'm integrating with respect to v. On the right hand side, I'm integrating with respect to t. So here I'll have limits from initial velocity to final velocity of the function that we have here with respect to v. On this other side, since we have time, then we'll say we'll start from rest to t of a with respect to t. So since we have nothing on the left hand side, there's no function there. So the derivative, or rather not derivative, the integral is just v. Before we do that, I want us to write like this. So we have the integral from the initial velocity to the final velocity, dv. On the right hand side, a is a constant, so let's push it outside the integral. From 0 to t, dt, like that. So the integral, there's a 1 here. Let me show you where the 1 is, in case you don't see it. There's a 1 here. There's only 1. Same thing here, there's nothing but just a 1. So the integral of 1 on the left hand side is just v. So v with limits from initial velocity to final velocity. Again, the integral of that 1 is now t, because it's with respect to time. So it's just t with limits from 0 to t. Now, on the left-hand side, let's replace that v with the final velocity first. So, where there's v, we'll replace it with final velocity, minus the lower limit. Again, where there's v, we'll replace it with initial velocity. This is equals to, where there's t, we'll replace it with t, minus, where there's t, we'll replace it with 0. So this gives us final velocity minus initial velocity, or this is equals to at. This is just a 0. So final velocity is equals to, so the initial velocity can cross the equal sign, so that it becomes like this, plus at, like that. So there we have it. This is the first equation of motion. So final velocity is equals to initial plus at. That's the first equation. To derive the second one, this is what we're going to do. We know that velocity is equals to displacement, change in displacement over time, right? If I cross multiply, this will give us dx is equals to v dt. So, I have an expression for v, by the way. But before we do that, let's bring in the integrals now. So on the left-hand side, I'll bring in an integral with limits from x initial to x final with respect to x. On the other side, I'll bring in the limits from time 0 to t of v dt, like that. Now, my main interest is this v that we have. Remember, according to what we did in the previous equation, v is equals to v initial plus at. So we're going to replace that v with that expression. So that is the integral from x initial to x final. This is equals to, sorry, there's a dx here. So where there's v, we replace v with initial velocity plus at from the previous equation that we just derived. Okay. So again, I want you to see the one that we have there. So on the left-hand side, if we integrate, we just get x with limits from x initial to x final. This is equals to, on the right-hand side, if we integrate v initial with respect to time, we get v initial multiplied by t. Integrating at gives us at 1 plus 1 divided by the same 1 plus 1. The limits from 0 to t. So this is good as saying x there, x initial to x final is equals to initial velocity. This here is at squared, or this is over 2. Limits from 0 to t. Now let's apply the limits. So on the left hand side, where there's x, I'll put final velocity, minus again where there's x, I'll put initial velocity. On the right hand side, where there's t, I'll replace it with t. Again, where there's t, I'll replace it with t. So now this over half can just be written as half a t squared. Okay, so I've replaced everything with t, but if I replace the t with a 0, everything will just be 0. So now what I have on the left hand side, that's final minus initial. So in other words, that's just the change in x. So this is equals to initial velocity times t plus half at squared minus 0. So the change in x, let's just call it s. So s is the change in displacement, in which s is equals to initial velocity multiplied by time plus half a t squared. So there we have it. This is the second equation of motion. Alright, so now let's derive the third one. So let's go back from where we started from. Remember, acceleration is change in velocity with respect to time. Now I want to separate this like this. Let me show you. So I want A, this is A, to be written as dv. I don't want to confuse you here. Here I'll put dx. Okay, now just wait for it. This is multiplied by another dx over the dt. So if you've seen what I've done, I've just introduced dt. We still have the dv dt as it is. dv dt is still there. I've just introduced the dx, such that if I cancel out dx, I'll go back to dv dt. So the reason why we're doing this is so that we can have it as acceleration is equals to dv dx. Now we know that dx dt is velocity. According to the previous equation, from where we started from, we said that velocity is dx dt. So this function that we have here, the dx dt, is just the velocity. So if I cross multiply here, this will give us a dx is equals to v dv, like that. Alright, so now that we've generated this, I think I prefer it the other way around, which is a v dv is equals to a dx. So let's just say something. So now that we've generated this, let's bring in the integrals. So on the left hand side, I'll have the integral from initial velocity to final velocity. On the right hand side, I'll have the integral from x initial to x final, like that. So if I integrate what we have on the left hand side, integrating v gives us v squared over 2, with limits from initial velocity to final velocity. This is equals to, if I integrate what I have on the right hand side, it will just be ax, with limits from initial to final. So now at this stage, it's just a matter of applying the limits, of which we can say where there's v, I'll replace that v with the final velocity. Then the same function, I'll replace v with the initial velocity. On the right hand side, I'll replace x with the final position, that is ax final, minus again with the initial position or displacement. On the left hand side, we can see that the 2 in the denominator is common, so we can just have it as a common denominator like that. So final velocity minus initial velocity. All this is equals to a x final minus x initial. I've just factored out the a. So this gives us final velocity squared minus initial velocity squared is equals to 2a. Now that bracket, x final minus x initial, is just the change in x. So final velocity is equals to, the initial velocity can go to the other side like this, plus 2a change in x. Now we know the change in x, let's just write it as s. So final velocity squared is equals to initial velocity squared plus 2a times s, which is the change in displacement. There we have it. So I hope it makes sense.